What's your handwriting? It is. Woo. All right, so I think I'll have to fix that. Okay, go ahead and record. Let's begin with a word of prayer. Got it? Okay, so I'll begin. Dear Father, we thank you for today. Again, we thank you for these students. Can you help us to just understand the material on the quiz and also a little bit more about improper integration together. Right? Amen. All right, you can go ahead and plug the mic in now. Let's see as we go from stereo to mono. Exciting troubleshooting. I once took a class in troubleshooting in my community college. The way it would work is we'd build a circuit, and then we'd have to leave the room, and then the professor would come in and mess it up, and then you have to figure out where it went wrong. He kept a host of these wires. What he would do is he would just sit in his office with a piece of wire and just go like this until he could break it inside the insulation, and then he'd plug that in somewhere. That's his go-to move. All right, so let me talk about the quiz. If you don't mind, for the sake of time, I'm gonna just talk about in words A, B, and C. Part A, this is a rational sequence. What's your name? Byers. So part A is a rational sequence, and so what do you do there? You divide by the maximum power you see on the top or the bottom, and what do you get? You get 1 because there's an n squared upstairs, there's an n squared downstairs, and so that works out to 1. A lot of you got that. Then number 2, part B, n squared sine of n pi. This is a trick. It's a trap. It's a dirty, rotten trick. What is sine of n pi? It is not 1.
0.
It is 0. Always. Forever and ever. Amen. So it's 0. It converges to 0 because that is just a really contrived way of writing the 0 sequence as to entrap Calculus 2 students who don't know what sine of n pi is. I hope you learned your lesson. Sorry. Well, I'm not so sorry that I won't do it again. But still sorry. Okay, so cosine of 2 times inverse tangent of minus n. Well, there the point is, right, that you can look at that as the composite of a couple sequences. So just to remind you, what does inverse tangent look like? Here's inverse tangent of x. It's just the graph of tangent, which has vertical asymptotes at plus or minus pi over 2. The vertical asymptotes flip the horizontal asymptotes in the inverse function. And so we have the limit as x goes to plus or minus infinity of inverse tangent of x is equal to plus or minus pi over 2. Likewise, by the continuous extension theorem, the limit as n goes to infinity of inverse tangent of plus or minus n is equal to plus or minus pi over 2. I'll let you think about that for a second. So when I look at part C, I'm looking at cosine of twice the inverse tangent of minus n. All right, so that is equal to, by the continuity of cosine, the cosine of the limit as n goes to infinity of twice the inverse tangent of minus n, by continuity of cosine. And also the fact that this converges to what? This is what? This is 2 times minus pi over 2, which is minus pi. It's by continuity of cosine, and the fact that 2 times inverse tangent of minus n converges to minus pi. But this, of course, is what? This is equal to cosine of minus pi, which is otherwise known as minus 1. So the answer there is minus 1. Look, I didn't grade your work. I graded your answer, with the sole exception of the last part, which is worth 2. So you get a check or you get an X. If you get a check, you get a point. If you got an X, you didn't. That's how this works, these kind of problems. Yes, sir?
I have a question about B.
B?
Yeah.
Yeah, sure.
So sine of n5 is 0.
Yeah.
But sine of n squared is infinity.
Uh-huh.
Would we have to take that out? I think I did that. I don't know if I missed that part, but I got the first part. I'm not sure how many.
Well, the thing is, it is true that n squared is going to infinity, but it matters not because a sub n is equal to 0 for all n. So it's the 0 sequence. Some people call this like an absolute 0 or something. I don't know. It's just a constant sequence, though, in disguise. Where was I? So what I was trying to say is, I told you on this quiz, I said find the limits, right? So that means that I was really just grading your answer for problem 1. Your work could be totally bonkers. I wouldn't care. I mean, I care. But I didn't try to search your heart and see why you wrote what you wrote. I just saw it's either 1, 0, minus 1, or it's wrong, you know? And I either wrote check or X. Of course, it matters to me, the explanations, right? But I'll ask you 2 kinds of questions. The one kind of question I ask is just find the limit, right? There you're free to just find the answer. I'm not going to quibble over your notation on those problems. If I say justify, on the other hand, I'm actually looking for complete sentences and a complete logical presentation of why the limit goes to what it goes to, right? What I'm showing you on the board right now is more closer to the end of the spectrum of justify, right? I don't really need to write all of the things I'm writing to find the limit. I mean, maybe I shouldn't tell you this, but I guess I have to tell you this. I mean, frankly, if you're really just after the answers, it's a pretty decent algorithm to just plug in 1,000,000 and see what happens. You know? If you plug in, what's that? That's what you do. Says the high score. I mean, so he has the high score, right? I'm sorry. I forgot it's not cool to be told. But you should listen to his advice. I mean, this is not a bad idea. Now, if I look at his paper, he didn't just write, I plugged in 1,000,000 into my calculator, the answer is blah, right? You didn't write that, did you? I will get you on the test. Let's see here. No, it really is. If you're uncertain of what's happening, plug in a number. You have calculators, right? So you can do that. But that's not the end of the story, right? Like for number 1, the rational one, you can plug in 1,000. You'll get like 1,000,000 over 1,000,000 plus some change. So you can see it's going to 1, right? But if you just plug in numbers and you say, well, it's like it's approaching, 1, or the limit is I forget. It's hard for me to remember what wrong things you said. But the limiting for part A, the limiting value is 1. It is not approaching 1. The limit is equal to 1. The sequence, right, a sub n is approaching 1. The limit is 1. Okay, see the difference? Okay, so moving on here. We'll get back to that. D, x to the n over n factorial. Well, that one, if you had remembered our discussion in lecture from section 11.4, this is one of our results. This is essentially a theorem that we can use, right? So if it's, certainly for a fine question, you could say, well, that goes to 0 because n factorial beats x to the n. Just game over, for any x. Exponential versus factorial. Exponential loses. You're just like, that's not an exponential function. Yes, it is. This is a function of n. X is fixed. It's the base. Here's an argument, though. If you didn't have that, if you had to justify it, it goes back to the homework problem. Remember the homework problem? 2 to the n, 2 over n to the factorial less than or equal to 4 over n? That argument will tame this problem. See, what you do is you just pick some positive integer k such that it's beyond the absolute value of x. Does that make sense that you can do that? If x is equal to pi, you could choose k equals to 4. If x is equal to minus 3,700,002, you could pick k equals to 4 billion. Whatever. There's always a larger natural number than your given real number. Agree? Because the natural numbers go on and on. And we're looking at absolute value of x. All right. So my goal then is to use a squeeze theorem because I know 0 is less than this, and I think we can tame this by we can make this smaller than something we already know how to take the limit of. So what you do is you just write it out, k times k times k times k times k, and n factorial, and then you look at the middle thing, right? If you know that n minus 1 is greater than k, right? You can make such an assumption because we're looking at the limit as n goes to infinity, right? So we can make n as large as we like. In particular, make it larger than k plus 1. If I do that, all of these fractions in the middle are smaller than 1. So if I replace these with 1 times 1 times 1 times 1 times 1 to 1 for those, then this is something larger than that. Sorry, that was an after-class discussion. Then I have that, which is k squared over n. But hey, for a fixed k, that goes to 0 because we have proved that 1 over n squared goes to 0 as n goes to infinity. Right? So I have this goes to 0. I have that goes to 0. I have the absolute value of x to the n over n factorial squeezed between them for n sufficiently large. So by the squeeze theorem, I get that the absolute value of x to the n over n factorial goes to 0. Right? But then, if you have the absolute value of a sequence goes to 0, that implies that the sequence itself also goes to 0, right? That's unique to 0, right? If we have the absolute value of a sub n goes to 1, what do we learn about a sub n? What's that? I don't think we even get that. Well, maybe. But certainly you don't get that a sub n converges, right? Because you could have the plus minus 1 sequence, so like 1 minus 1, 1 minus 1, 1 minus 1. The absolute value of that's constant and is 1. But the sequence which oscillates between plus or minus 1 doesn't converge. It never zooms in on 1 or minus 1. Any questions? Again, here all you had to do was write down 0 for the quiz. And the test will be a mixture of find and justify, all right? All right, so the next one, part E, this is an indeterminate power. A lot of you got this one. By the way, generically speaking, you guys beat the earlier section pretty severely. I think by about 2 points on the average. A lot of you guys have 5s. That is rare air in the earlier section. N squared plus n. And so what you do is you use the continuity of the exponential and properties of the log to bring down the 1 over n. Call this thing star. L'Hopital that thing. After you extend n continuously, that gives us 2n plus 1 over n squared plus n. And then do algebra, divide by the maximum power of n in the top and bottom, which is n squared. And this is 0. Then you take that 0, plug it back up in here, and that gives you e to the 0, which is 1. Again, some non-trivial subset of you got that right. Woohoo. Any questions about that one? I think it's worth pausing to just kind of smell the roses here for a second. How do rational sequences go? Can we just kind of like take stock of what's the general story? If you have something like Pn over Qn, what happens? There's basically 3 things, right? 0, infinity. 0 categorically happens if what? If the degree of what? Yeah, if the degree of Q is greater than the degree of P, game over, right? That means the denominator is strictly larger. You've got like a raw Well, you can, if you divide by the max power, you've got just 1 over n or 1 over n squared kind of stuff upstairs going through the steps. So the top goes to 0 and the bottom goes to something finite. So 0 over something finite, 0. So if the degree of the numerator is strictly smaller than the degree of the denominator, it goes to 0. Vice versa, this, if the degree of q is less than the degree of p, right? So in other words, if the numerator is a larger degree than the denominator, that's going to either go to plus or minus infinity, right? When does it go to plus? When does it go to minus? Well, the plus if the sign of the leading coefficient is positive, minus if the sign of the leading coefficient of the numerator is negative. And then what's in between is if the degrees are equal, right? If the degrees are equal, then you've got something like, let's say, q sub n, or rather p sub n over q sub what? M, let's say. Maybe n and m are the bad letters. Let me say k and l, I don't know. Where p of n is equal to p to the k, n to the k, plus da da da, plus p naught, and qn is equal to, let's say, q sub l, n to the l, plus da da da, plus q naught. And what do we know about k and l? More specifically, they're equal, right? So I've made a mess of it, sorry. In other words, the degree of p is equal to the degree of q. Now, at the moment, so that's useful, right? If you're just looking at something and you're just trying to find the limit, those 3 rules of thumb can quickly calculate the limit of a rational sequence without doing more writing, right? Like I can do something like 13n plus 27n cubed minus 7n squared divided by n plus 1 plus 3n cubed. And if you look at this, right, what I'm saying is you can immediately say that that goes to what? It goes to, oh, look, they're equal, 27 over 3. Answer is 9, right? That is the logic I would like you to leave this course with. It shouldn't take a lot of time to do one of these, right? Now, you know, if I say justify, you got to show your steps, right? So how do you justify it? Divide, right? Divide to n to the power 3, the top and bottom, and then you just use the limit laws, basically, right? Like this step is the justify. I mean, I'll let you get away with that. Even that, I mean, some purists would say you should include a few more steps and say which limit laws you're using. I don't care. I'm sorry. It's enough. This is enough. All right. I digress. But I think it's important to just stop and take a step back and you should have that kind of big picture of these. These shouldn't be something, you should know where you're going with one of these before you start doing algebra, right? I think most of you do, so. Oh, okay. Glad to help. Okay, so then, moving on. F, we have cosine of n squared plus 8 over n squared. This is pretty much like just your garden variety squeeze theorem problem, right? So you start, you're like, okay, so minus 1 less than cosine n squared plus 8 less than 1 because it's cosine. That's true forever and ever. I could put pretty much anything in here, right? As long as it makes sense, and it'll still be between plus and minus 1. Then I divide by n squared, which I can do because n squared is certainly a positive quantity if n is an integer, positive integer, right? So it doesn't destroy the inequality. And then I could do squeeze theorem because this one and that one plus or minus 1 over n squared go to 0, right? Hence, the middle thing, cosine of n squared plus 8 over n squared, goes to 0 by squeeze theorem. This is a justification for why that goes to 0. Again, if you wrote down 0, I give you credit because I just said find. I didn't say justify. Does that make sense? Okay. This one, you do L'Hopital's rule on this guy. Extend n to be continuous. You got infinity over infinity because I told you a and b were positive. A lot of you messed up the differentiation because you forgot that the inside function's an, right? So you divide by an, but you know what you also have to do? You also have to multiply by the chain rule. So there's a lot of you who messed that up and somehow got a over b here. That's a common mistake. But as you can see, the b over the b and the a over the a, well, they be canceling. This is 1. It goes to 1. The limit's 1. Okay? That is totally unsurprising if you know your properties of logs. The log of an is log a plus log n. And the log of bn is log b plus log n. So if you do L'Hopital's rule on this thing, these constants, natural log of a and natural log of b, differentiate to 0. So if you did L'Hopital's rule to this, you'd get 1 over n divided by 1 over n immediately. Right? Now, another way you could look at this expression, right, you can see what's going on. As n gets really, really large, well, natural log of a and natural log of b are nothing. They're tiny. So it's just basically asymptotically, that's certainly just natural log of n, upstairs and downstairs, and so they match, it goes to 1. Yes, sir?
Can I divide both the denominator and the numerator by natural log of n, and then justify it by that way?
What? Why? Wait. What?
Divided both the top and the bottom.
Now, you want me to start with this one, or which one? This one.
Yeah.
So you're saying this is equal to, right? You're like natural log of a over natural log of n plus 1 over natural log of b divided by the natural log of n plus 1. Okay, then what? 0. No, why is that 0? Yeah. Ah, hey, nice. Indeed. Now, as I told the earlier section, I've showed you one path to most problems. Remember when we were doing integration, I was always like, you could do it this way, or you could do it that way, or you could do it this way, or you could do it that way. A lot of that, right? Not so much of that right now. I've just been showing you one path. Now, somebody earlier, in a similar note, said, hey, couldn't you also take this and like L'Hopital that thing, right? And I was like, well, yeah, you could, right? This would be 2 over 2n plus 1, and that would have been another path to 0, right? And sometimes it's nice to think about L'Hopitals when we can do algebra too. Only someone very strange would think to do algebra where we could do L'Hopitals. But it's a good kind of strange. It makes sense. I know who brought you here. I don't know. So you met. You said you met Min, right? Min Win. Yeah. He may have the honor of being my strangest student ever. I was very privileged to be in the presence of Min during 2 things. One thing is the Lego movie came out. I never saw the Lego movie at this time, but Min was always singing "Everything Is Awesome" all of the time. And that was in retrospect very hilarious. And also, Gundam style, Min did the horse dance. It was amazing. But Min has done a number of other interesting things. I like Min. Min's now at Penn State, but anyway, I digress. Where were we? Oh, the last one. N squared e to the, yes, oh, I'm sorry, yes.
Did you skip a step? So after you do L'Hopital's on G,
Oh,
So don't you have to do L'Hopital's again?
no. These are actually, this actually is algebraically equal to 1. The 1 over n's cancel, the a's cancel, the b's cancel. Like this is 1 over n divided by 1 over n. That's just 1.
But an and do it.
It's still pizza over pizza. It's just 1. I mean, it's... That is the constant sequence 1, written in a weird way.
Okay. Well, my question is because then you can say that's just infinity over infinity. I mean, I know they're different.
But it's not, I mean, fine, but this is an algebra step.
Okay.
This is equal to 1 over n divided by 1 over n, agree? Which is equal to n over n, which is equal to 1. But I say once you have this, you can go straight to that, because you've got the same thing upstairs and downstairs.
If you have the same infinity over the same infinity.
There's no infinity. I'm not talking about infinity here. It's n. 1 over n divided by 1 over n is 1. That's true whether n is 2 or it's 2 trillion. I mean, that's an algebra step.
I mean, I understand.
It's like that n squared sine n pi problem earlier. The fact that n could be a kabillion squared doesn't matter because sine of n pi is 0. Game over, end of story. Sine of n pi is 0. It's not limiting to 0. It's not approximately 0. It is 0. This is not going to 1. This is not approximately 1. This is stone cold 1 for any n in the positive natural numbers. So, I mean, there's no need for other things.
Okay.
It's okay. I mean, I know you guys are battling with various uncertainties and misappropriations of logic, let's say. I'm not saying you specifically. I'm just saying the class as a whole. I just graded your quiz. I see you guys are in an intermediate state. You're tending towards where you want to be. You're not there yet, right? So, yes.
So n over n is 1 because you haven't plugged in. So
I never plug in infinity. And I never plug in infinity.
I know you don't plug it in. I understand that.
Yeah.
Because you don't plug in anything, you're taking a limit.
That's right. That's right.
But you're approaching infinity.
No. But like, you see there's a 1, and you plug in infinity for n, but there's no
Any number divided by itself is equal to 1.
I'm going to go on. N squared e to the minus n. We could talk after class. N squared e to the minus n is n over e to the n, right? Extend n continuously, L'Hopital that thing, 2n over e to the n. L'Hopital again, 2 over e to the n. Now, plug in infinity. And we get 2 over e to the infinity, which is like 2 over infinity. I mean, fine. I mean, you guys got me. It is true that these are useful heuristics, right? I can't deny it. I mean, it is true that, but don't write these. Don't let a math teacher see you write these because it makes us angry. And you don't like us when we're angry. Think those things, don't write those things. I said you can think it, just don't write it. Unless you're in an engineering class, and in that case, it's your proof. But limit as n goes to infinity of n squared e to the minus n is equal to 0, is what this shows, right? It's a fun noise. All right. So anyway, you guys are making good progress. You still have work to do, obviously, but all is not lost. There's still hopefully plenty of time before Tuesday. Tomorrow there's likely to be snow. It is entirely likely this class is canceled tomorrow. We'll see what happens. If class is canceled, you should turn your homework in my mailbox, which is in the math department, which is over there, right, in the 4th floor. I have a mailbox Friday, as soon as you can get here, before the end of business. If the class is canceled all day long, then I will collect homework Monday, but we still have a test Tuesday. I will just post a solution, and I don't know what that means, but I'm going to post a solution because I want you guys to study the solution for homework 5 come tomorrow, right? So, what can I do? If it snows, it snows, but we still have a test Tuesday. All right. So that brings us to the topic of improper integration, I can erase this stuff now. Woohoo! All right. So improper integration, I've already showed you a few yesterday, right? And basically, it's just the same song and dance with a limit put in front of things. And so when do we say an improper integral converges? The improper integral converges if the limit, which is implicit within the integral, does what? Goes to infinity. No, the opposite of that. We say it converges if the limit exists and is a number. We say that the improper integral diverges if the limit does not exist. We say it diverges to infinity if the limit grows without bound as you approach the whatever it is you're approaching. Is there a question? Yeah.
What do we say if it's something like a sine function?
We'd say, well, okay, so if a limit doesn't exist, right, you can say that the limit doesn't converge. But in the world of limits that don't converge, there are different kinds of failures to converge, right? Some limits which don't converge go to infinity. Some go to minus infinity, right? Something like sine, as x goes to infinity, sine of x, I would say that diverges due to oscillation. Just like the minus one, like plus minus one sequence, I would say that also diverges due to oscillation. There are other forms of divergence, but those three are the main ones. But if I want you to clarify the mode of divergence, then I would add instructions something like explain whether the limit converges or diverges, and if it diverges, explain the divergence as best as is possible with our standard terminology or something like that. But I didn't do that on the quiz anyway, but that doesn't, stupid. What was our example we were working on? Hopefully that answers your question. Okay, so we were trying to find k such that the integral from minus infinity to infinity of k over 1 plus x squared was equal to 1. Now if we can do that, that makes f of x equals to k over 1 plus x squared, a so-called probability distribution, right? This is just a fun application. So the way you do this is something like this. Integral from 0 to infinity, k dx over 1 plus x squared, plus the integral. So we want 1 equals to this plus, oh, I'm sorry, I should do minus infinity to 0 first. It doesn't really matter. I mean, the sum of two numbers, it doesn't really matter which order you write them in, but just for the sake of not being weird, I should write them in the order I'm writing them. Okay? This is essentially the definition. Well, I mean, fine. So much writing. So this is by definition these two. Well, I mean, it's not written in stone. You have to split it at 0. I'll explain why here as we go on. Our goal right now is find k to make this happen. Make it so. Okay. All right, so you guys know, how do we define those? Well, that's the limit as, let's say, t goes to minus infinity of the integral from t to 0 of k dx over 1 plus x squared, plus the limit as s goes to infinity of the integral from 0 to s of k dx over 1 plus x squared. It doesn't really matter what you use here to denote the limiting process. You just need to use some letter. I used s and t. You could use a and b. There's really only one letter, maybe two letters you shouldn't use here, which are what? K and x. Very good. Yeah.
Now, what I would do is
Yeah, but that wouldn't be, but that would be something else. That would be the principal value of this integral, which may or may not be equal to the integral. The point is that these limits have to be taken separately. If they both converge, it is true that the principal value will match that value. But you can deceive yourself by doing that. For example, you can calculate the integral from minus infinity to infinity of x dx and go like, okay, so that's the limit as t goes to infinity of the integral from minus t to t of x dx. So that's the limit as t goes to infinity of 1/2 t squared minus 1/2 t squared minus t squared, right? So that is 0. What you said is equivalent to what I'm doing.
Even if you split it with like a 0.
But that is not correct. It is true that the principal value of this integral is equal to 0. This is actually the principal value. But the standard definition of improper integral says that this area is 0. It's not defined if you go to plus or minus infinity. Now you could say, well, you're going symmetrically to plus or minus infinity, then it's 0 because you've always got as much area to the right as you have to the left, right? But I'm just telling you, the standard definition is that you have to approach the plus infinity and the minus infinity separately, not at the same rate, which is what you're insisting when you write t and minus t there and there and there. Okay, digression. Yes?
So the pieces that they're still equal to 1?
Yeah, I want all of this to be equal to 1. That's that. Bless you. So, what we have here is we have k times inverse tangent, right, of 0 minus k times inverse tangent of t plus the limit as s goes to infinity, right, of k times inverse tangent of s minus k times, you guys have all kinds of interesting questions in this section, inverse tangent of 0. Like sometimes I think I'll cover more in here, but then when I get here, you guys ask me questions and I don't get as far. It's a good thing. Questions are precious to me. Oh, yes, certainly. So you could say, well, why did you divide the integral at 0? Why did you break it up at 0? Why not use 3 or pi or some other number, right? Would it matter? I mean, think about this graphically for a second here. What I did, right, is I said, well, this area under the 1 over y equals, k over 1 plus x squared function, basically the idea is it's this area, right, which is this. And then this area, which is that, right? What would have happened if you split it somewhere else in the calculation that follows? Like, suppose I'd split it, say, here at C. So I had like this, like over here area plus over there area. That would have just put a, that would have put a C here and here, right? And at the end of the calculation, you'd have inverse tangent of C, right? And you have inverse tangent of C over here. And so in this calculation, they would still cancel. Because you get plus 1 here, you get minus 1 here. And this generically will happen in these improper integrations. So that's why it doesn't matter where you split it, because in the end, when you actually calculate, those things will cancel out. Because it doesn't really matter if you say that it's the area from here to here and then all the way out to infinity, or where you divide the left and the right. That said, for my choice here, inverse tangent of 0 is just straight up 0, right? So what we get, just a second, I'll come back to your question. So what we get is that we have what? This is what? This is minus pi over 2, right? this is pi over 2 because of inverse tangent. Remember, limits to plus pi over 2 or minus pi over 2, depending on whether we're going to plus infinity or minus infinity. And so we've got ourselves k pi. Set that equal to 1. Our choice of k is, in fact, 1 over pi. Now, what was your question?
Yeah, what if the original equation was 3x over 1 minus x squared?
Well, that would be a very different problem. So everything I'm just saying, I'm assuming that the function's continuous on the reals. If it's not continuous on the reals, if it has a point where it's not defined, as would be the case with k over 1 minus x squared, k over 1 minus x squared has vertical asymptotes at both plus and minus 1. I would have to integrate from minus infinity to minus 1, then from minus 1 to 1, and then from 1 to infinity. I'd have to calculate those three improper integrals separately and see what happened. Being that those are essentially partial fractions tells me that's basically like 1/2 1 over x minus 1 over x plus 1, something like that. I know that the 1 over x thing diverges. That's going to diverge, if nothing else, because it's got reciprocals inside. Now, the at infinity, it'll probably be okay, but it's the vertical asymptotes that get you with that one. Because minus a minus pi over 2 is pi over 2 times k, and then plus pi over 2 times k, but a half plus a half is 1. So therefore, f of x equals to 1 over pi times 1 plus x squared is a probability distribution on minus infinity to infinity. So there you go. I like this example. It's kind of fun. You know, it's got interesting limits in it. It's not that calculationally bad, right? Yes, sir.
Can you explain the purple to the black again? Like, where you simplify it?
So let me first of all get rid of the C. That was a side comment. All right. Then what's your question?
Like, how you simplify it into the inverse tangent. So, to negative infinity is negative pi over 2.
Yes.
How you
So
simplify to get
this, that's 0. That's 0. This whole thing, minus gives me plus k pi over 2. Right? This is going to minus pi over 2. That's minus k. So this is k pi over 2. This also limits to k pi over 2. But k pi over 2 plus k pi over 2 is k pi. So just a word on notation. If you look at the integral from, say, 0 to infinity of e to the minus kt dt. All right. So here's a notation I have seen in engineering classes that I have taken. I will see this. So that's e to the minus kt divided by minus k. I evaluate that from 0 to infinity, right? And that's equal to e to the minus k times infinity divided by minus k plus e to the 0 over k. Minus gives me plus. But that's like e to the minus k times infinity over minus k plus 1 over k. I'm assuming k is greater than 0. And of course this is, that's 0. So the answer is 1 over k, right? That is a popular notation in physics and also in engineering. But we don't do that in here because this is a math course and we have to use proper notation. So what our solution would look like is something like this. So we take the limit as, let's say, s goes to infinity of the integral from 0 to s, e to the minus kt dt, right? Well, that's the limit as s goes to infinity of e to the minus ks over minus k plus 1 over k. And then if k is greater than 0, So, it's a question of how you want to communicate limits. The problem, of course, with writing infinity as if it's a number is it tempts you to do things which are crazy, right? It's very tempting in that kind of notation to when you see 0 times infinity to go, well, 0 times anything, 0, so and that's, you're like, well, I know that 0 times infinity is just a notation to implicitly denote a limit of one thing that's going to 0 and another thing that's going to infinity, and I know that I should use L'Hopital's rule to try to discern what actually happens, right? Well, if you're such a person, it's reasonable for you to use this notation, right? But not in my class. Okay. I will say, I actually would allow this kind of notation in a later math class even, but I'm a bit of a heretic as far as math goes, so. All right. Okay. Oh, okay. So, just a word on notation. Now, the next thing to talk about, of course, is the comparison test. In terms of section 11.7, there are really maybe three major events. The first event's already happened. That's how do you define an improper integral? What are they? What converges, what diverges? I hope you have some sense of that from our discussion so far. The second thing is the comparison test, all right? The third thing is the this theorem here, all right? So I'm going to talk about the comparison test, then we'll talk about this theorem, and those are the major players for that section. All right, so here's the comparison test. If you have f of x and g of x continuous functions from some point a on out to infinity, all right? And you have that, you can compare them in this way. F is smaller than g, and they're both non-negative, okay? They could be 0 at some points, but they can't be negative. And that's true for all x beyond some point, beyond some a, all right? So I suppose graphically it looks something like this, right? It can do all kinds of crazy stuff, but it's stuck below the g. Here's y equals. The point is g is always above, f is always below, and 0, neither of them can go below 0 beyond some point x equals to a. I mean, who cares what happens over here? Over here, it can do all kinds of crazy, whatever, doesn't matter. Point is beyond a, behaves. All right, if that's the case, then if the integral from a to infinity of g converges, then the integral from a to infinity of f likewise converges. Your book doesn't say this right here, but in fact you can say a little bit more. In fact, you can say this. You can say that in this case you actually have this. The integral of f is less than or equal to the integral of g. Those are both real numbers. You can compare them. The integral of f will be smaller than the integral of g in this case. On the other hand, if the integral of the smaller function diverges, then the larger function must also diverge. And given the data here, they both diverge to infinity. Okay? Your book doesn't quite say it as concretely as that. I'm adding this statement. They both go to infinity. And I'm adding to you that actual inequality because I think it's useful to say that. Don't worry, I'm not going to prove this, but if I was to, basically that example we did the other day with comparing, remember we had the integral from a to b of f of x is like between the lower bound times b minus a and the upper bound times, b minus a. Basically, if you take that sort of theorem and you can say the definite integral of f and g are related in this way, property of definite integrals, and then you just feed that inequality of definite integrals into the limiting process, and through properties of limits, basically the Squeeze theorem for limits gives you this. It's but anyway, I won't prove it in here, but it is in fact true. All right. Now, in order for a comparison test theorem to be useful, you need something to compare to, right? So the standard grab bag of examples, a really useful collection of examples is given to you by these 1 over x to the p integrals. For example, the integral from 1 to infinity of dx over x to the p if p is not equal to 1. How does that work out? By definition, that's the limit as t goes to infinity of integral from 1 to t of dx over x to the p. That's just definition, right? Next step, well, that's really x to the minus p, right? So the antiderivative, I add 1, and then I divide by that power. So x to the minus p plus 1 divided by minus p plus 1. Then I evaluate. So I got t to the 1 minus p over 1 minus p minus 1 over 1 minus p. Then I got to think about cases, all right? If p is greater than 1, that means that 1 minus p is less than 0. If 1 minus p is less than 0, what happens to this limit? It's like 1 over t or 1 over t squared, 1 over the square root of t, 1 over t to the pi power, whatever you want. It goes to 0, right? As t goes to infinity, this goes to 0 in the case that p is greater than 1. On the other hand, if p is less than 1, then that is a strictly positive power up here. So that would be like the limit of t, or the limit of square root of t, or the limit of cube root of t, or limit of t to the 14th, whatever it is, that thing goes to infinity as t goes to infinity. And so there are your cases. Converge, diverge. What about p equals to 1? Special case, right? P equals to 1, you got the log as the antiderivative. So you end up with the limit of log t minus log 1, also infinity. In summary, we have that the integral of 1 to infinity of dx over x to the p converges to 1 over p minus 1 if p is greater than 1, and otherwise it diverges. This is very convenient because it gives us this like go-to example we can compare other integrals to, right? So, does the comparison test tell you what the value of the improper integral is? No, that it does not, but you can still use it to do things. So here, as an example, check this out. If you look at f of x equal to 1 over 1 plus x squared, surely that's less than or equal to 1 over x squared, right? Because I did what? I made the denominator smaller. So, hence, the integral from 1 to infinity of dx over 1 plus x squared is less than or equal to the integral from 1 to infinity of dx over x squared, which, by the way, is 1 over 2 minus 1, also known as 1. Well, this is fun. I feel like if we ever had a war, I'd already be ready to like teach. Like, I've already taught in wartime. It's like always wartime here. See here. Yeah. Everyone duck under the desk. I don't think it really would help much. I mean, these desks, I don't know. But I love these desks. I would so prefer taking a class on these as opposed to those awful chair desk things, don't you think? Yeah. They're so much better. Yeah, that physics room has other problems. That fan is just sucking the life out of me. Hey, we do momentum today. Woohoo! I love momentum. All right, so this doesn't tell you what that is, right? But it gives you I mean, we can straight up calculate this too, right? What's the integral from 1 to infinity of dx over 1 plus x squared? Limit as t goes to infinity, right? Integral from 1 to t. So it's the limit as t goes to infinity of inverse tangent of t minus the inverse tangent of 1, which, by the way, is pi over 2 minus pi over 4 which is pi over 4. So, in fact, that estimate is spot on, right? Pi over 4 is a number less than 1. Right. So this comparison test, it actually does give us some information about the integral. It doesn't tell us what it is, per se, but it's something. So how are you going to apply the comparison test in interesting ways? What's the game you play? How about this one? Integral of dx over x, I don't know. Well, how about ln x? Plus x, maybe, I don't know. So let's see here, 1 over ln x. I may have to change it to sign here. I want 1 over x to be less than this. That's not true, is it? So what I want to look at is x minus ln x. That's more fun. Don't worry, you guys don't have to make up examples. You just have to understand them. Okay, so, well, I don't know. Every so often I ask give me an example of question. Those are usually depressing to grade, though. I've done what? I've made if x is greater than... So look at this one, right? Like 1 over x is less than or equal to that, right? Because what did I do? I made the denominator smaller, right? So this awful function, which I for sure don't want to integrate. Do you know how to integrate 1 over x plus log x? I don't know. I mean, it's kind of on the cusp of something maybe I could do. I don't really want to try, though, and I don't have to, because this is smaller than that, right? The integral from 1 to infinity of dx over x is infinity, which implies that the integral from 1 to infinity of dx over x minus log x is also equal to infinity, because I just showed you there's a smaller function than it, which has a divergent integral. So if it's larger than something that diverges, guess what? It also diverges. So if you're just focused in on the question of converge or diverge, make or break, this is really useful when you combine it with this example, and then plus our usual bag of tricks, making denominators larger or smaller to make things, the fractions, what did I say, larger, smaller, so smaller, larger. It's reciprocal. Where's my silly phone? All right, well.
Can I tell a joke?
I got 3 minutes, so yeah, you can tell a joke, sure.
Great. An infinite number of mathematicians walk into a bar.
First one says, I'll have 1 cup.
Uh-huh.
Cup. The next one says, I'll have half a cup. The next one says, I'll have 1/4 cup.
Uh-huh.
The next one says, I'll have an 1/8 cup.
Finally, the bartender just pours 2 cups and says, "You mathematicians ought to know your limits."
That's true. That's right. That's exactly right. See what he's saying is 1 plus 1/2 plus 1/3 plus 1/4. Is it? You said wait. How many cups? How many?
Infinite.
So 1 plus a half plus a plus a 4th plus a what? 1/8. 16th. Okay, so if you look at this, this is really